Okay, here we are with the Unit 2 test review video. Hopefully you participate and check this thing out. Helps you a little bit for the test. So it looks to me like here's the test topics, questions 1 through 7, and you get a little bit of taste of each of these throughout the course of the video. Here will be the topics that we talk about: sigma notation, area under the curve, solving complex equations, piecewise functions, and evaluating functions. You'll get a little bit of an idea here of what is expected. First, we have summation notation. Two problems that could possibly show up in the test will be similar to this. So first, expand this argument here from the index beginning at 1 to 4. So what we would be doing there is plugging in 1. Remember, it is a sum, so we're adding each of these together. 2, 3, and 4. It does not say evaluate, it just says expand, so that's enough. Another type that you might get would be like this one down here, where it says write the given expression using sigma notation. You could also see summation notation. Alright, so the 0.4 here is constant, it's out in front, it's unaffected, so that's going to be part of our answer no matter what. Obviously we're going to need the Greek letter sigma to represent that we're adding up a sum here. And then the next piece we want to look at here is within our equation, okay, or within our expression here, what stays the same the whole time? Well, there's a fraction with a numerator of 1. That stays the same, therefore that should be in our equation as a constant. Now the only part about our equation that's changing is the denominator, starting at 2, 2.4, 2.8, 3.2, 3.6. You could go about this a few ways. We could call 2 the first number in this sequence of numbers, which means we would have to go backwards one time to get our 0 value to write our equation. Keep in mind we're writing an mx plus b. Okay, or we could let 2 be our 0 value, which means that it is our starting point, and the growth is very simple. Here the growth is growing by 0.4 each time, so we would end up with 0.4k plus 2. All right, because we're using 2 as our 0 value, we must start at 0. All right, so if we start at 0, 1, 2, 3, we would end at 4. Now there are variations to that. We could start at 1 and go to 5, but we'd have to have a 1.6 there, you know, etc. However, that would be a sufficient response. Next, we have area under a curve. This is sort of like the meat of the chapter. So here's a sample problem. Given f of x equals x squared plus 3, find the area of f from 3 to 6 using 5 left rectangles. I give you no steps here, you know, to solve this. However, on the test, you will have, you know, first do this, then do this, okay? First step is to find the width of each rectangle. And we do that by subtracting the domain and dividing by the number of rectangles. So 3/5 ends up being 0.6. Okay, now we're starting at 3, so if I was graphing this, I want to break my graph, and I would start at 3, and then I'd go to 3.6, and then I'd have 4.2, okay, 4.8, 5.4, and 6 will be my final value. Let me get my calculator. So remember, using the calculator here, we're going to go to y equals. We're going to type in our equation, all right, which is x squared plus 3. All right, and then we want to set our table up to match what we're looking for specifically. So our table is going to start at 3. It's going to count by 0.6s. Whoops, 3. And it's going to count by 0.6. And then I'm going to go to my table, and I'll get my values here that I can plot. So 3, 12, 3.6. So on and so forth. You see here that I'm going to have to change how I label my graph. Okay, it looks like I need to go from 12 to 40. Picked a great example here, Mr. Warner. So I'm going to have to break this graph. I'm going to say that this is 12. Okay, I need to get to 40. Looks like here I'll make this 10, 15, 20, 25, 30, 35, 40. So I'll plot my points then, my first one being 12. I remember that. The second one was 15.96. Let me go in. I know the last one was 40. Let me flip back over here. Shame I can't have this up at the same time. 20, 26, and 32. So 20, 26, 32. Right? So there's the section of my parabola that I'm going to be finding the area for. I'm using left rectangles. So that means my left side needs to be touching the line. So I would sketch those in. I would shade that because I'm not finding the entire area. This is an approximation. These actual values are important. 12, 1596, 2064, 26 something, I forgot that one. 04 and 3216. So 2604, 3216, and the 40 doesn't matter because we're using left rectangles. So the actual area itself would be found by summing the area of each of these rectangles. So I would have a width of 0.6, and then I would add up each of my heights, which I just get from my table. Right, and that will give you my area. I would also want to write this in sigma notation. Of course, you have an area formula. As long as you typed it incorrectly, that should also give you your area. So I'm going to have 0.6, which is my width. That's all the time. I'm going to write my function, x squared plus 3, except I'm not going to write an x. I'm going to write how x is changing and where it starts. So my x is changing by 0.6, and it's starting at 3. 0 to 4, because left rectangles are always 0 to n minus 1. Right rectangles are always 1 to n. N is the number of rectangles. And then finally here, I actually want to calculate the area. So I end up getting, for my area there, 64.08 units squared. So that's sort of what you're going to have to do there. I will lay it out for you in a little bit greater detail and tell you specifically each of these steps. Find the width, write the sum, draw the graph, write the sigma, find the area. Is this an upper or lower bound? It is lower, simply because we have some missing space here between our rectangles and our curve. It has nothing to do with the fact that it's a left rectangle, just because our rectangles are below the line. Next, it looks like we're going to talk about solving complex equations, ones that we have been struggling with a little bit, where x is the exponent. This is an Algebra 2 review topic. We've got to get better at it. All right, so first things first, I want to write both of these as exponents. This right now is written as a root. Remember, we can change any root to an exponent by simply putting the root in the denominator of the fraction. A square root is a fractional exponent, or not a square root, but any root is a fractional exponent. And then I still have 1/25, so the x minus 2. Now, the only way I know how to solve this when I have x's in the exponent besides a logarithm, which I'm not going to use today, is by writing common bases. So I'm going to write 1/25 as 5 to the negative second. Now, nothing else about this changes. I'm going to try to color code it accordingly. So the x minus 2 doesn't change. The 5 to the x over 3 doesn't change. The reason I'm doing this is because once my bases are the same, my exponents must also be equal. So I come over here and sort of start a whole separate problem. X over 3 has to equal negative 2 x minus 2. And I solve this equation. X over 3 equals negative 2x plus 4. I'm going to get rid of my fraction by multiplying by 3. So x is going to equal negative 6x plus 12. So 7x equals 12. So x equals 12 sevenths. By my calculation, you can always plug it back in to check your work if necessary. Next, we have piecewise functions here. All right. So given this piecewise function, 2x plus 1 for x is less than or equal to 1, x squared minus 2 when x is greater than negative 1. So graph them a section at a time. I'm going to do the 2x plus 1 here first. So 2x plus 1, starting at negative 1, is going to start here, up 2 over 1. But x is less than 1. So I picked a bad graph here. Hold on a second. All right, we're back here. So 2x plus 1 when x is less than or equal to -1. So that's going to put me right here to start at -1. My slope would be up 2 over 1, right? But I'm less than -1, so I go down 2 over 1 to get my remaining points, right? And then I draw my line. Okay. So it's going to look something like this. All right, and then let's see here. I'm going to do my other section here, which is a parabola x squared minus 2 when x is greater than -1. So let's see, a downshift of 2 for that parabola. Okay, so there'll be a point there. There'll be a point right here. So it looks like it will be continuous. And if I draw that curve, it would look like this. Okay, so there's my piecewise function graphed. At least my original. Now it's asking me to graph h of x minus 3 plus 2. So I'm going to go right 3 and up 2. What's going right 3 and up 2? Everything is going right 3 and up 2. So the cool thing for me is I actually have the capability just to do this, but I'm not going to play those tricks on you. I'm going to go ahead and move it right 3 and up 2 for all my points. There's my parabola section. My line from there is going to go down 2 over 1, just like it did before. And then I want to write my equation of my new piecewise function. Now you can do that a couple ways. You can just write the equations of those two pictures, or we could just use our originals and plug the shift in. So 2x minus 3 plus 2 plus 1, and x minus 3 squared plus 2 minus 2. Now if you wanted to simplify those, that's perfectly okay with me. Lots of variations here. We could go just one step simplify, where we combine the 2 and the 1 here, and then the 2 and the -2. Okay, or you could actually distribute this 2 and simplify this further if you wanted to into just a linear equation. Keep in mind we have a new domain because it moved to the right 3. I'm talking about when x is less than or equal to 2, and when x is greater than 2. So that would be a key component there of rewriting the equation of the new function. And it looks like here we have evaluating functions. This is the final. So we have the function g of x equals 2x squared plus 5x minus 12. We want to find each of these. So if we're just finding g of -2, that's simple. That's something we've done before many times. We're just plugging in -2 into our function, and we're evaluating that. Keep in mind, though, that the -2's should go in parentheses, and if you do that correctly, then you would you'd be able to find this equation very easily. However, if you don't put your -2 in parentheses, then you might run into some difficulties there. So it looks to me like we get -14 for that. The second one here is the same thing, except now instead of plugging in -2, we're going to plug in an a plus 1. So we have 2a plus 1 squared plus 5a plus 1 minus 12. Now you must simplify that. Just plugging that in is not good enough. We need to simplify it. So order of operations applies. So we need to do this first. So 2. Keep in mind that it's not a squared plus 1. It's a squared, double the inside, 2a, square the last number. We can distribute the 5 minus 12, and then we can distribute our 2 here. So I end up with 2a squared plus 4a plus 2, and then I still have my 5a and my, let's see, that'll be a -7 now. Combine like terms, so in the end, I conclude with 2a squared plus a 9a and minus a 5 is what it looks like I end up with. Okay, so you will have, an a, sorry about that. You will have a's in the answer. Last, it says g of x equals 0. So there we're letting the equation be 0. All right, which technically means we're finding the zeros of the equation, the roots, so x-intercepts, whatever you want to call it. So factor that If you need to use the box diamond, please do, but eventually we should be able to get to a point where we can do this in our head. 2x and x. Now we're looking to multiply to get negative 12, but also when we add, we need to end up with a 5x. Okay, so let's see here. It's going to be a 3 and a 4, so let's say a 4 here and a 3 here. That gives us 8 and 3. That's how we get the 5. The 8 has to be positive. The 3 has to be... Sorry about that phone call. So let's finish this up. 2x minus 3 equals 0. So x is going to end up being 1.5. And then finally, x plus 4 equals 0. So x ends up being negative 4. Those would be your roots for that. So take a look at this. Hopefully it helps. And if you have any questions, bring them first thing tomorrow. We're going to take this test. Good luck.